Before we look at how we use the relationship between heat and temperature to solve problems related to heat flow, I want to give you kind of the initial toolkit that you're going to use when you're solving problems related to what we call calorimetry, chemistry experiments that relate the temperature change in a sample and the mass of the sample to how much heat is flowing into or out of the sample. And so the first thing we want to talk about is we want to review the units that we use to measure energy. And some of these units are units that you may have been introduced to earlier in the term. The main SI unit for energy is the joule. So almost all the energy measurements that we make in class this term or in lab will be measured in either joules, capital J, or kilojoules, lowercase k, capital J, where 1 kilojoule equals 1,000 joules. And a joule is a common unit of energy or work in physics, and it's related to the energy required to accelerate a mass of a kilogram to meter squared per second squared. From a more practical standpoint, a unit of energy that we use every day, traditionally, particularly in America and England, the calorie was used as a unit of energy rather than the joule. And of course, the calorie is still, from a nutrition standpoint, how we measure the energy content of our food. Now, there's a little bit of a small issue in units that you have to be aware of. Traditionally, 1 calorie, or by the strictest definition, 1 calorie spelled with a lowercase c is equal to 4.184 joules. So a calorie is a larger unit of energy than a joule is. It takes nearly 4 joules to give you 1 calorie of energy. However, when we talk about calorie in a nutritional sense, we're actually talking about calories with a capital C. So if you look at, say, an energy bar or a coffee that you're taking away in the morning, and you see that there are 200 calories per serving in the energy bar or 250 calories per serving in whatever you're eating, when you see calorie on a nutritional label, that's actually a calorie with a capital C. And what calorie with a capital C indicates is kilocalories. So there's 1,000 calories with a lowercase c in one typical nutritional calorie. And so 1 calorie of food energy that you would get from food is equal to 1,000 calories, which is actually equal to 4,184 joules. So a joule is a unit of energy that is much, much smaller than the calorie that we typically talk about potential energy in. Occasionally, to solve problems in class or lab, we'll use the relationship between calories and joules if we absolutely need the answer to our energy problems in calories. But in chemistry and physics, because the joule is the SI fundamental unit for energy, the energy, particularly in our case, the heat flow into or out of a system, is going to be measured in joules or kilojoules. Another important property of energy, including heat energy going into or out of an object, is that it's a special property which physicists and mathematicians call a state function. The total energy of a system, or the heat energy of a system, is what we call a state function. And a state function is a tricky but very useful mathematical concept where it's a property of a system that depends on the current conditions, not how you got to the current conditions. And so what this means is when we talk about energy problems, including heat flow problems, we'll talk about initial and final conditions. We'll talk about where did the system start, like what temperature did it start at? Where did the system finish? What temperature did it end up at? And based on the difference between initial and final temperatures, we'll be accurately able to calculate the energy gained or lost by the system. That's because energy is a state function. I can talk about how much energy had to be lost between point A and point B as long as I know where point A and point B are relative to each other. And this is going to simplify the math that we need to calculate the difference in energy between a system at one point and a system at a new point quite a bit. State functions can be hard to visualize, but kind of in a chemistry laboratory setting, if I have a chemical dissolved in a solvent, like for instance, if I have the inorganic chemical hydrogen tetrachloroaurate, this is an ionic compound dissolved in 50 mils of water at room temperature, the energy of that system is going to depend on the temperature, the physical state of the chemicals, the identity of the chemicals, what this compound was, and the sample size. How much of this compound I dissolved in water and how much water I have. It's not going to depend on how much I stirred it or whether I heated it up and cooled it down and heated it up and cooled it down again and let it come to this final temperature. The energy of the system at any point just depends on what are the conditions of the system at this point in time. And the difference in energy between the system at two different points of time simply depends on what's the difference in the conditions, particularly the temperature, between this point and that point, not the path that it took to get from the initial to the final conditions. One way to visualize a state function, which may or may not be useful to you, is to think of a state function as like the distance between two places. And no matter how you choose to get from point A to point B, the distance between point A and point B doesn't change. So for instance, if you were going to drive from Portland to Denver or Denver to Portland, there are multiple paths you could take. You could take this interstate or you could take that interstate. You could make more stops or you could make fewer stops. You could spend more money or less money to get there. So you could drive between Denver and Portland. You could fly between Denver and Portland. You could take a train between Denver and Portland, or you could take a bus between Denver and Portland. You might choose to stay in a hotel some nights. You might choose to camp some nights, depending on the season. So things like the amount of time it takes you to get from Portland to Denver, or the amount of money that you spend getting from Portland to Denver, are not state functions. The amount of time or the amount of money it takes to get from Portland to Denver depend on your path and the choices you make along the way. But the distance from Portland to Denver does not change unless the Pacific Ocean, the Pacific tectonic plate breaks off the Pacific coast and sends Portland into the sea. Portland and Denver are going to stay basically the same distance apart, no matter how you choose to get there. And so when we talk about the energy difference in the system, or the heat lost between the system at this state and the system at that state, it's like we're talking about how far apart or is Portland and Denver as the crow flies. That's a state function. Position is a state function. Time spent to get from point A to point B or money spent to get from point A to point B are not state functions. And mathematically, it turns out to be really a lot simpler to calculate the difference in energy because energy is a state function. Okay, so we're going to pigeonhole state functions for a little bit until we talk about enthalpy. And I want to start talking about how we measure heat flow and speak to the actual mathematical difference between temperature and heat. Because remember, I said those were related in the previous lecture, but they're not the same. Figuring out the heat flow, the amount of heat gained or lost by the sample in a chemistry environment, is based on an experiment known as calorimetry. And calorimetry is a standard experimental approach that we use to measure enthalpy changes, or what for now we're just going to call heat changes associated with a reaction. And the thing to remember is that temperature change can be related to heat change, but they're not the same. You need an equation that relates the change in temperature to the change in heat. And what types of things relate the temperature change of a sample to the amount of heat energy gained or lost by the sample? Well, it depends on the sample's mass, how much of the sample you have, and how well the sample conducts heat. If a sample is a poor heat conductor, it's what we call a thermal insulator, it's going to take more heat to raise the sample's temperature. You can think about this in practice as if you have a pot of boiling water on the stove, it takes a lot of heat to heat the water inside the pot to boiling, as opposed to just heating up an empty pan until it's too hot to touch. Copper, iron, and various metals that make up the pan are poor thermal insulators. They're good heat conductors. They heat up really fast. Water is actually a really good thermal insulator, which we know instinctively because when it's hot, we look for water to cool down, because even if the air gets very hot, the temperature of the water doesn't change that much just because the air is getting hot. So you can relate temperature to the amount of heat energy gained or lost in a sample through a constant, which we call the heat capacity, capital C. And the relevant equation is that the heat gained or lost by the sample Q is equal to the heat capacity times the change in the sample's temperature, which we call delta T. Remember, delta is our usual chemistry symbol for change in. And the heat capacity is a constant value which depends on your material and the mass of the material that you have. And it's the amount of heat that is needed to raise the temperature of the system by 1 degree Celsius. Your heat capacity, capital C, would have units of joules per degree Celsius. So this big proportionality constant, the heat capacity C, is something that you can look up in tables. In practice, though, it's a little simpler to use a related constant, which we call lowercase c, which we call the specific heat. So in chemistry, we're usually dealing with a pure substance or a very dilute aqueous solution when we're talking about a chemical reaction. And we can rewrite this expression instead as the heat gained or lost by the sample Q is equal to the mass of the sample M times a new constant, which we call the specific heat of the sample, C, times the change in the sample's temperature, delta T. So these x's here, these are multiplication signs. In practice later on in this term, I'll omit the multiplication signs and I'll simply write what we call the calorimetry equation as Q equals mc delta T when we're solving problems. I'm just emphasizing that the heat gained or lost by the sample is equal to the mass of the sample times the specific heat of the sample times the difference in temperature between the initial and final state of the sample. So when you're solving problems, if you want to know how much heat is gained or lost by a sample, the information that you need to have at your fingertips is the mass of the sample. You need to know how much the temperature of the sample changed, and you need to know what the specific heat of the sample is going to be. Because the specific heat, lowercase c, is a different value for every material that's out there. The specific heat, lowercase c, has units of joules per gram degree Celsius, and it's based on the amount of heat required to raise the temperature of your sample by 1 degree Celsius for every gram of the sample that you have. Materials or solutions that don't conduct heat very well, that are thermal insulators like water, have high specific heats. Good thermal conductors like metals tend to have low specific heats. And to give you an idea, water has a really quite high specific heat, particularly for a molecular compound, and it is 4.18 joules per gram degree Celsius. A typical metal like copper has a specific heat that's almost 10 times lower, something around like 0.4 joules per gram degree Celsius. So this is the fundamental relationship between heat energy gained or lost and how the temperature of the sample changes. So kind of our culminating exercise for today is we're going to go through some examples where we show you how you can use this equation to figure out how much heat energy was actually gained or lost by a sample that's heating up or cooling down. And this is the fundamental equation through which we connect the temperature change of a sample to the heat gained or lost. To make this equation work, we need to have a specific heat for every substance that we might be dealing with. And your textbook has a table of specific heats. You can also find them online. Be careful with your units though, because when we're solving problems in this class, we'll generally want specific heats in units of joules per gram degree Celsius. So you need to watch your units because some tables will also have specific heats given in joules per kilogram degree Celsius, and some tables will have specific heats given in calories per gram degree Celsius. So if you go to your textbook, your specific heats should be in the right units. If you just pull a specific heat off of the internet, you'll have to double check that the units are correct for the calculation that you want to do. And almost 100% of the time in class, we are going to be dealing with specific heats that have units of joules per gram degree Celsius to solve our problems, because the mass will be in grams and the temperature change will be in degrees Celsius, and we want the answer, the amount of heat gained or lost, in joules. But in general, if a specific heat is not given to you in the problem, the move is to go to the table in your textbook and see what the specific heat for the system that you're interested in actually is. This problem-solving approach, the Q equals mc delta T equation, is going to be something that we come back to again and again, particularly next time in lecture when we talk about calorimetry experiments. The last thing we want to do today is give you some practice with just using the equation to calculate the amount of heat gained or lost by a sample, or to calculate the specific heat of the sample if you know the mass and the temperature change of the sample. So check those out and conclude today's activities by trying the discussion questions at the end of today's materials. If you have any questions, please look for me during our kind of appointed question and answer class time, or find me during office hours. And I'll see you back here in a few minutes for the example problems.